The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Welcome back to the podcast. Sebastian here with you for another solo episode. Today I'm coming to you from the IEEE International Conference on Quantum Computing and Engineering at the Palais de Congrès in Montreal, Quebec, Canada. This is an excellent conference put on by IEEE Quantum, IEEE of course being Institute of Electrical and Electronics Engineers, which is a professional association formed in the 60s, I think, that covers a bunch of different areas within the field of computer science, computer architectures, system architectures, electronics engineering, that sort of thing. They recently formed IEEE Quantum. They've been putting on this conference for, I think this is the fourth year. They started during the pandemic, if I recall correctly. And it's a really interesting program because they're purposefully bringing together the sort of ingredient fields that are coming together to create quantum computing. So physicists, quantum information scientists, information science specialists within computer science, computer engineering, system engineering, and in particular, high performance computing and supercomputing specialists and communities. And that's really interesting because looking forward, there's physics challenges that still face us. There's engineering challenges facing us, fabrication, et cetera. However, if we anticipate having quantum computers that actually are useful for certain purposes, the next set of challenges will be deploying those devices in useful solutions. And those solutions are going to include, and Kevin and I have spoken about this in the past, classical compute resources in addition to quantum computing resources. And making all of those heterogeneous resources work seamlessly is going to be really important because there's no point in gaining some kind of performance advantage from a QPU if then the integration with the CPUs sort of evaporates that advantage and ends up being the same overall system performance. And so that's a really strong topic within the Quantum Week talks, and even there's forming birds of a feather sort of interest groups. And I think there's even progress and discussions of sort of eventual standards around how to integrate quantum and classical compute resources, which I find really fascinating. And today's guest actually is really directly involved in those efforts. He's Martin Schultz. He's a professor at TU Munich, or Technical University of Munich, and also on the board of directors of the Leibniz Supercomputing Center. And in his roles at TU Munich and at LRZ, or the Leibniz Supercomputing Center, he's really leading a set of efforts around this kind of effort to define how quantum and classical resources are going to be integrated into meaningful and productive solutions. So we grabbed a room that was very kindly provided by the IEEE Quantum Week organizers. And we had this following conversation, which I thought was really interesting. So let's take a listen. I'm here with Martin Schultz. We're at the IEEE Quantum Week in Montreal, Canada. And we were going to have a conversation about the work that Martin has been leading in his capacity as sort of one of the leaders of the Munich Quantum Valley effort. So Martin, tell me about what was the sort of initial impetus that caused that sort of set of activities to start?
So the Munich Quantum Valley is a large effort across multiple institutes, multiple universities. So it includes Fraunhofer, Max Planck, TU Munich, where I'm located, the Ludwig Maximilians University, the Erlangen University, DLR, and then also the Bavarian Academy of Sciences, which then includes the Compute Center as well in Munich. And so this is a large effort that was born out of the Bavarian high-tech agenda that's pushed by the state. And they kind of wanted to establish the quantum science in Bavaria with a very large grant, and it was then supplemented with other grants, also from the federal level, from the EU level. So there's a lot of stuff that came together. And it started from the physics side, like most quantum projects started, with the idea of having multimodalities being developed in Munich or the Munich area, and pushed it up. And then the question came, how do we connect this to the world? How do we make this available? What do we need in addition to just the pure hardware? And that's where we started talking more and more about software. And to be honest, in the beginning, it was a little bit of an afterthought almost, because it was a pure physics idea. Well, most of these projects are in the beginning. And it became clear very, very quickly that we need more than that. And so we started building a software stack, connecting it to a web portal that we can access things like we know from most quantum systems. But then very early on, we already thought, well, the web portal alone won't help us that much. We need to do this in a way that we can support a wider workload, and quantum will be always very specific. I mean, we had the conference, we heard this in several talks as well. It's a very specific thing, which it hopefully can do very, very well, but we need to have the rest connected to it. So hybrid workflows, need to connect it into high-performance computing, HPC. We heard this morning also in another keynote, a lot of connection also to AI. And then how can we tie these three things together and make them really work together? So quantum and HPC integration was high on our agenda from the very beginning on. We started with activities there very early on with both sessions at various conferences. We have a workshop now that's in its fourth instance, so bringing people together. Also, that started, of course, very slow, because it's wasn't people's forefront in the beginning, but it's coming more and more. And we're really seeing these communities grow together, which is kind of exciting.
That's very exciting. And do you think, in part, that perspective came from, I mean, LRZ is a supercomputing resource that's very heavily used by the academic community, as well as in collaboration with industrial R&D, I think, as well, right? There's sort of industrial collaboration projects that go on it.
So it has a very, very strong and strict public mission at the moment. So the projects have to be public and basic research. Industry we're working with industry in collaborative projects. So there has to be always an academic partner with it, and it has to be a funded project from the outside. But then we have some industry collaborations as well. But that's actually one of the challenges we're looking at right now. How can we open this up to have more industry involved? Because we have requests from industry. We want to try this out. We want to get things going. We want to see how much this works for us. And that's actually kind of a challenge right now. How can we fit? It's not so much a technical challenge as a political and societal challenge. How can we make this work, and how can we get the right bylaws in place to do this? And we're pushing in this direction right now.
No, I mean, it's what I find fascinating is, you have you're thinking over the horizon of getting these QPUs to the state that they can actually do useful work, and you're thinking about what does that end-to-end solution look like? And I think you're not alone in that. There's certainly a lot of efforts in the public sector, but in many ways, I think you've got a head start on everyone. It seems like you're quite a bit further along this road. I mean, you've got an operational superconducting device from IQM now, and you actually have running a running pipeline that combines classical and quantum hardware together for at least the obvious use case, which is a variational job where you're using the two in conjunction, right?
Right. So we actually managed to do a first shot between the HPC system and the quantum. So one of the quantum systems in direct connection there. And so we have been getting to this. We have this concept, as our quantum team calls this, as a series of hero runs. So we have these goalposts that they're trying to reach and really shooting for, and they managed to do this connection between the HPC system and the quantum system in a variational thing, very closely connected, very very integrated. They were just a couple meters apart from each other, basically at this point, which is kind of the exciting part, right? But yes, we've been trying to do this we've been working towards this goal for a while, and to be honest, also the emphasis has shifted. Right in the very beginning, it was, how can you take a system and put it in a data center, right? How do you even hook it up?
Right.
Or what kind of environment do you need? How do you deal with the false floors, which we have in centers, which is terrible for quantum systems because they're shaky.
Lots of vibrations.
Vibration, exactly.
The opposite of what a classical system cares about.
Exactly. And so also even if you have it on a floor, on a solid floor, how do you put in together then the right water? They need slightly different water chemistry, different water temperatures. How do you get the right power together? How do you hook the networking together? We focus at the beginning very much on the hardware side just to get this thing going, and then we had some duct tape of software in between them just to make it work. And there was a very early project that was funded by the Federal Ministry for Research. And there we actually didn't buy a quantum computer. We actually worked with IQM on buying all the individual pieces and putting it together on our own. There was a very strong collaboration where IQM helped us really put these things in the right place. But our team actually worked with them hand in hand to install all the microwave cables and all these kind of things. So we learned basically how this works, right?
That's such a valuable set of experiences, and really there's no substitute for putting one of those devices together. They're kind of a magical combination of science and technology right now.
Right, exactly.
It's really tough.
And so we learned a lot in this part of the project. And now the more newer systems we quote unquote buy, the hardware of course is not that easy. It's not like you buy a rack, plug it in and run it. But there's more like of a consumer seller relationship, a vendor relationship. Now we bring these things in and put them up. But we still have all the expertise from back then, so we know what they're bringing in and we understand that technology. And so as part of that, we have now actually 3 systems running. There's one production system running, that's the one you were referring to. It's a 20-qubit system called QXA. There's a German demonstrator project. And we have 2 R&D systems also in our R&D lab. It's the Quantum Integration Center that the local team has been standing up and maintaining. That's been really a real huge asset to have like the systems right there. There's an HPC system right next to it as well. And we can still plug and play. It is not a production system in that sense.
Is that also superconducting?
So we have 2 superconducting R&D systems in there, one 5-bit, one 20-qubit. They're actually in the same fridge. So we're using them, the fridges more as racks at this point and not as separate systems.
That's
which
cool.
I think this is the trend we will see more and more. And then earlier this year, beginning of the year, we also got in an ion trap system. So we definitely want to look for multiple modalities.
Is that from an existing vendor, or is that a...
Yes, there's a system from AQT, Alpine Quantum Computing, which are very close partners with the Munich Quantum Valley. I mean, they're just an hour and a half away, so this is kind of the nice thing in this sense. That kind of rounds off the modality aspects of the Munich Quantum Valley, which was always superconducting, ion traps, and then also neutral atoms, which we also have a working relationship with a new vendor that's a spin-off of the Max Planck Institute in Munich. And they're also on track installing a neutral atom system at the Compute Center as well.
And are these systems sort of, you call them R&D systems, is there sort of access into the system itself? So, some vendors, their system might be treated as a black box, and you can send your circuits and you get your results, but you don't really know what's going on inside. Is this more of an open system to sort of mirror the open software development efforts that you're doing as well?
So that's perhaps a little bit longer story. So yes and no, but like it always is, right?
Yes.
In the beginning, of course, when we set this up, we started working with the vendor software stacks because that's the only thing that was there, and we started looking in them. And also, when vendors were really early on this as well, so we had a lot of conversations on how these things could look like. We tried to understand each other's software stack. That's when we really focused still on the hardware and how to bring the hardware in and set it up. Since then, we have shifted the focus since. I don't want to say quantum systems got commodity, but we have these vendor relationships. There's a service, there's an agreement. When you bring this in, there's a contract. There's an acceptance procedure for these things now, and then the hardware is there, and we know how to hook this together on the networking side now. So the focus shifted really onto the software now to really make these systems efficient, workable, and this is going to be the huge work going forward to kind of get this HPC QC integration going.
Right.
I think without the software efforts, we won't get there because we really have to connect these pieces here in an efficient way that's easy to use, that is also seamless, that requires work on the quantum side, but also on the HPC side to really have this integration part. And there we kind of have like a stepwise approach because we don't want to, there's no way to kind of run ahead here. We're working with the vendor software stacks for now. They're working on special access nodes, which are already tightly integrated into our HPC systems. And then we have our software stack basically on top of that. And then backend connectors into their commercial software stack.
I see.
And that is kind of a trade-off for now because that still leaves a lot of work to do on the vendor side. And then we have our stack on top of that.
Right.
And the idea now is to work with the vendors to slowly migrate these heavy vendor stacks into something very thin and low level and push this over to the other side.
Interesting.
And that stuff is working. A lot of these contracts that we have when we buy these systems have in there that this transition has to happen. And to be honest, the vendors we're working with are very open for this. We have regular conversations on this. They're interested in having an interface into the compute center that is standardized, so they can actually sell a system and everybody can just plug it in and is happy with it. I don't think they want to maintain their own software stacks and the infrastructure.
I always say, use your PhDs to work on the qubits. That's the hard part, not the classical software stack. We have people that do that. Those are solved problems.
Well, it's also the hard part, right? But for a different group of people, you're absolutely right. There's a different expertise there. And
physicists writing code.
I won't comment on that.
So are there existing frameworks or code bases that you've been leveraging? I mean, I know, Kik, Cubic, Kibo, those are all sort of, they have control platform, open source control platforms, but also Kibo's got a whole set of open source libraries. There's open source projects from the Unitary Fund, for example. So there is sort of it's a small but growing community of existing open source technologies. Have you used any of those in your development?
Bits and pieces. So we're starting to bring things in where it makes sense. The base infrastructure that we have, we're actually leveraging open projects from the HPC community or from the classic compute community.
Slurm?
We do leverage Slurm. That's a separate story we can come back to. We're thinking whether Slurm is sufficient for us or whether we need some more on that.
I just like to say the word Slurm. It's a funny word. I don't know.
Well, and if you like, there's the other ones we're looking in is a schedule called Flux, which is out of the DOE labs.
Okay,
Livermore. So Flux or Slurm, we'll see.
Yeah.
But yeah, we need a more scheduling approach that kind of allows us to do this integrated scheduling.
Right.
But that's still an open question of where we want to go. And there we're watching very closely other software projects on the pure HPC side that need similar techniques, similar software components, and we don't want to do anything separate. We want to kind of fit into the ecosystem. So there's a tight relationship there to other software projects as well to make this work.
And I mean, things like scheduling, those tend to be more batch or less performant dependent, sort of like it's queuing up and using the resource when it becomes available. You also mentioned AI, and also obviously the whole topic of state preparation or error mitigation or error correction. All of those need, I think, really, really high performance and tight integration between classical and quantum, so that you don't incur overheads that eliminate whatever quantum advantage you might get from the quantum algorithm. What sort of integration strategies do you have in mind for those sort of tight, more demanding kind of use cases?
Yeah, so there's going to be different time levels and time loops, basically. As you said, there's different granularities that we need to have. And so from the very coarse grain, we're going to start with the job scheduling systems, where you said you want a quantum system, you want to have access to that. Use prediction mechanisms that allow us to predict when resources are free and how can we overlap different jobs. And then there will be kind of an intermediate level scheduler, that's kind of at least our vision right now, which then actually does the decision once there's a kernel to offload, which system actually does it go to, where the free resources in that sense. And then you're absolutely right, then there will be another level, because we think of a hierarchical multi-level scheduling, where towards the device side, you will have these very tight feedback loops. And the question is how much we can, how tight are these loops? As in some technologies like superconducting, we may not be able to do this purely in software. You have to push things in hardware because the loops are so tight. Other technologies like ion trap, they're a little bit slower and have other qualities instead of that. And then we may be able to bring it into software. And our goal is to develop the software stack in a way that it actually can run on the HPC system itself and connect the HPC system directly to the control.
Like making RPC calls or something too.
Perhaps even lower weight than that, to really directly drive this from there. And then you can actually run a feedback loop directly into your HPC system where you have the resources, where you also can use GPU acceleration or FPGA acceleration on the node itself.
Interesting.
And for technologies like Ion Trap, I think this will allow us to bring us a lot of stuff in.
And neutral atoms as well, right?
And neutral atoms as well, exactly.
The lower clock speeds, that makes a lot of sense. But you're right, something like superconducting, you're probably looking at something like, quantum machines DGX or whatever, where there's a GPU that's actually part of the control system that can do things like error correction at a speed that makes sense for that.
But even then, you may need another intermediate loop for some kind of conditional executions and things like that you want between the device selection and this low-level part. So we have potentially another level of scheduling in between here. So this hierarchical scheduling that really informs from the coarse grain to the fine grain and has this common overview, I think will be really a key technology. And that's some of our teams are working on that right now.
That's really great. How large is the effort? How many people are actually writing code with you?
So, and this is again a very difficult question to fully ascertain. The whole Quantum Valley is about 350 people working on it, but that includes all the physics parts as well. The software in total, I would say, is about 35 FTEs.
Significant open source effort, definitely.
And there's a large part in the compute center at LRZ. There's a special team, the quantum computing department, which has these people and which work directly on the machines and which are also a little bit more geared towards the software development. And then we're working with the university side, where a little bit more the researchy side is. And we're finding this avenue of how to take research, harden it, and then put it into the stack.
And is there any thinking about like integration of cloud-based systems, for example, in classical HPC, there's an idea of bursting out to the cloud if you need additional capacity temporarily. Is there sort of a similar kind of thinking around maybe a specialized QPU for some aspect of a workload in the future, obviously, when these things can do productive work? Is there kind of that thinking as well, that remote or cloud-based resource?
That is possible. So the software stack itself is relatively flexible, as modular, as you can plug in different components. And at the end, there's a series of backends. And it is also not only intended for us in Munich. We would install this on the HPC system, as I mentioned, to have the stack running on the HPC node itself. But that's not a must. You can run the same stack also as a cloud service or on a separate system if you want to, depending on what your compute center setup is. And one of these backends could also be a remote backend to another system. If that's the setup you want. You can also mix and match that, obviously.
That's great. And I'm just imagining, because I think that we're going to see probably more diversity in hardware efforts in the future rather than less, because we're still in this very exploratory stage. So the idea of being able to stand up an experimental qubit or experimental system in a university somewhere and still be able to use it in that integrated kind of environment is very powerful, I think.
So we're actually using this also inside the Munich Quantum Valley, because we said we're developing also the valley is developing also these computers. So the Max Planck Institute for Quantum Optimizing is doing neutral atoms. And then there's the Walter Meissner Institute, who's doing superconducting qubits and also experimental qubits there as well.
Exactly,
and those will never be at the compute center because they need it in their labs.
Exactly.
And so we have already in the stack to those one a connection. We demonstrated this from the HPC system, going to a small demonstrator at Walter Meissner as well across campus. That works.
Excellent.
Don't get all the benefits of the tight loop and the integration, but it works and is there for research.
It's more about the efficiency, right? If you can not have to replicate all the work you've done to do those integrations and just tie into it. It doesn't matter necessarily that you don't get the performance, as long as you're being able to reuse those tools and those frameworks. It's just shortening the time to actually get it into the hands of the people you want to experiment with it.
Exactly.
So that's exciting. So at what stage do you think you may be making some of this code available to a broader set of open source communities?
So we're thinking about this doing relatively soon. We have a first repository open. To be honest, this is not one of the most exciting repositories yet, but it was a starting point. But the idea is to open this up in the coming months, I would say.
That's exciting.
particularly focusing first on some of the interfaces that we need. We have an interface definition that works for the vendors, how to hook in. We're working currently with selected vendors to get first feedback, and this is one of the first things we will open up to get broader feedback.
Yeah.
Perhaps even kind of a sort of a standardization going around it, or homogenization, let's say it this way.
That's what I wanted to ask you is how do you balance, I mean, you need standardization in order to make these types of frameworks work, frankly, right? I mean, you have to agree on standards in order to be able to make systems talk to one another, but we're also in this very early stage where there seems to be far more unknowns than knowns at this stage of quantum computing. Yeah. So is there something in your architectural design that's sort of baking in that uncertainty, that's making it like maybe easy to pivot in the future if something new comes along?
So we're trying to do that. Yeah. I mean, this is prediction of the future, right? Yes. We don't know. But a lot of us were involved in large software efforts and standards efforts in the past, where we've seen how this evolved over time. So personally, I'm involved in the message passing interface standard, the MPI standard, and I've been leading the MPI forum for a while now. And we have seen really how something that was initially intended to be the right thing has kind of morphed over time with new technologies. Right. And then we were able to retrofit the standard, and sometimes looked a little bit clunky, but it worked fairly well. But I think we have learned in this process also how do you design something in the beginning to actually, what you just said, allow for these uncertainties to happen. And we're trying to learn from this and bake this into the interfaces. That's great. But then also, be honest, right now, we are not yet afraid of breaking things as long as we don't break it too much. Right? So there's still, we won't release a 1.0 version very much on purpose. It will be 0.1 or 0.2. Yeah. And by the time we get to 1.0, that's where we're going to start freezing and have a more formal change process in place. But right now, I think it's more of an experimental thing. We're getting feedback from everybody, and we're making this in stone.
That's smart. That's smart because, I mean, I think, there's potentially more diversity coming down the road in terms of the execution models and maybe in terms of the intermediate representations. And certainly, everyone has sort of a general assumption that we're going to be climbing up the abstraction stack. So it may end up not, passing around gates and circuits, but something higher level abstractions that are actually how you describe your workloads, right? So that flexibility is important, I think.
Yeah, and also for the intermediate representation, we're trying to work here also very much with the community and looking into standards that exist that have started coming up. So LSE joined the QIR consortium to kind of see there, well, how can we extend this? How can we make this use? A lot of our stack for the middle part is already based on QIR or is being transformed to be based on QIR. But then you're right, I think where we have the most uncertainty is actually towards the higher end, towards the abstractions. And nobody knows really what there will be, right? I think that's a really huge push forward right now. But then once they can get it into a QIR and then our compiler can pick it up, then I think we're getting a little bit more on safe waters, and that's kind of the interface we're trying to establish.
That's another topic, compiling and transpiling. I mean, there's so many differences between, it feels like to get optimum performance from any particular piece of hardware, you have to be very, very conversant in the exact idiosyncrasies of that hardware.
Correct.
Like, is your compiler sort of also architected to be extensible, so you can have extensions that are hardware specific? Yeah. Okay.
Yeah, absolutely. It has to be this way. Yeah. So what we are trying to do, and what I think we have achieved, is a core infrastructure that is completely agnostic of the particular technology in the back, which allows you to basically take a circuit, get a circuit through a pipeline, change things on the fly, and at the end have this interface to the back end part. And to be honest, it's not even particularly not even quantum specific, right? This is a disaggregated accelerator with just-in-time compilation, which something on the computer science side we have had other examples for, and we're trying to retrofit onto that.
Ways in which we can show the physics community that we're not, we may not get some of the stuff you're talking about. We're pretty smart too.
It has to be a give and take, right? I mean, we have to work together in this one.
Exactly.
And this has perhaps even been the most fascinating things over the last 2 years. I can come back to the software in a second, but I just want to put this in here. In the beginning, when the Quantum Valley started, it was really the physics community and kind of us on the computer science community trying to talk to each other. It was totally different languages. Yes. If you talk about a benchmark, they meant something totally different than what we mean in a benchmark. And also there was not an idea of this is difficult what you do on the other side as well, right? And in the last 2-3 years, particularly in this Quantum Valley where we had everybody on the same campus, we had regular meetings. We had what we call technical exchange meetings, where we brought people from the physics side, from the electrical engineering, from the computer science, all together into one room. We established a common language, we established a common understanding. We also, became clear we all need each other in the right way. And these interfaces has been established, and that has been the most fascinating part over the last 2-3 years, that we really grew into one community that can take this on.
That's the part that absolutely keeps me completely fixated on this industry, because it's exactly that. I mean, it's not only have we rewound the clock to hand setting registers, like we're right down at the metal, so we get to repeat the entire evolution of classical computing, which is fascinating in and of itself. It's like, what if we did classical computing over again, but we had the cloud and open source software and higher level languages already, right?
Exactly.
And then added to that, we also get to have this dialogue with the science community, the physical sciences, opening their eyes to what we can do to help them along this journey. It's a fantastic set of challenges and sort of intellectual puzzles to solve.
Absolutely, and that's also why I like this conference where we are right now, the Quantum Week, which has exactly this. It's not a physics conference, it's not a computer science conference, but it really brings people together, and I think also that helps establish this common language and the cooperation that we need.
Exactly. And I think the IEEE is very smart. I've seen this conference evolving over the last, whatever it is, 4 years now, and it is exactly that. It's carving out that middle space, and now birds of a feather sessions of the type you described with Oak Ridge or other supercomputing centers, all collaborating around these discussions, are now leading to, as you said, potentially early standardization discussions, which will just take more of the friction out and more, and enable more innovation on top of the work that's going on.
Exactly.
So
yeah.
that's fantastic. So. Back to the birds of a feather thing. Do you have sort of a first international collaborator partner? Is it like an Oak Ridge or another center out there that is sort of waiting for the release of your software to try to join into the collaboration?
So we definitely have interest from partners to look into this, to most particularly to work on the interfaces with us.
Right.
So we've been talking to a lot of partners, including in the DOE, but also in the German ecosystem. Yeah. Also in the European ecosystem, there's a lot of effort going on there as well. On how to homogenize this. Particularly in EuroHPC, there's this, and as you know, this program of these first 6 quantum computers being seeded by EuroHPC. One will be in Munich in the Leibniz Supercomputing Center. The tender is still out, so we don't know yet what it's going to be, but it will be what we know as superconducting system as well. But there's 5 other centers, and the EuroHPC made it very clear we want one software stack, not 6. Yeah. And we're working towards that. There have been regular meetings within Europe as well, and so that's kind of our target for the software stack to bring out. But then also larger, we're really trying to push the idea of HPC-QC integration. There is a working group as part of the IEEE quantum work that we also have above here, and that's really very broad. That includes already Oak Ridge and Los Alamos National Labs and iCheck in Ireland. Right. Yeah. And then plus Laura Schultz from LRZ, and then myself from the TUM side.
Great. We've got to get ICE involved from Japan as well. They're building out their GQuad center.
Yeah, so we have been talking to the Japanese community as well. They have been a part of our work. We need to make this international, right?
Absolutely.
And for this working group, the 5 of us are really just the starting point. Yeah. And we want to broaden this out, and so that's why the BOF session on Thursday here hopefully will help to bring in more people. Excellent. And the idea is at some point also start our own workshop series on this, to kind of bring more and more people in. Yeah.
I'll be there.
Excellent. Wonderful.
Well, thank you very much, Martin. I think this is an excellent effort, and I'm really impressed. As I said, I was at the tutorial last year, and the ideas were great, but I had no idea you were going to make this much progress in 1 year, so very impressive.
It was a very busy year, but it was a lot of fun. Yes.
That's great. Thank you very much. That's it for another episode. Hope you enjoyed it. Thanks for listening. I wanted to add that I've been working on a book for O'Reilly Media on the history of the field of quantum computing, its origins, where it came from, the progress that's been made to date, what people are working on, what the current status is, that sort of thing. It's an extended explainer of sorts. The book will be out in 2025, but the first 12 chapters, which are really the foundational understanding of the field and the history of the field, the roots of the field in quantum physics and in classical information theory and the early development in the 70s and 80s and 90s, that's all online right now on O'Reilly's learning platform. They wanted to release it as an early preview while I'm still working on the last 5 chapters. As I said, it'll be out in 2025. But if you're interested in checking it out now, go to newquantumera.com. That's all with no spaces, newquantumera.com. You'll find a link to the podcast there, and as well, I've added a link to the book now. So check it out. Let me know what you think. I'm interested in any feedback you have, positive and negative, and I hope you enjoy it, and we'll see you again soon on the podcast. Thanks for listening.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.